Thank you. Dear colleagues, let us introduce the article Risk Assessment of the Software Development Process Using Fuzzy Algorithmic Approach by Hanna Rakitianska and Bogdan Prus, Vinnytsia National Technical University, Ukraine. The main goal of software development is to provide the best quality product. Traditional reliability growth models predict software failures but do not allocate efforts to prevent them. Developers need interpretable reliability models that give them insight into how to distribute effort to reduce the risk of defects. Process mining is a set of methods aimed at extracting basic knowledge to interpret data and establish interdependence of events and processes. Describing the uncertainty inherent to development processes leads to the use of reliability models based on the algebra of processes and fuzzy logic. The use of traditional risk analysis models, such as fault trees, is limited by complexity of system behavior. The use of state-based models, such as Markov chains, is limited by the growth of the state space. Methods of statistical inference demonstrate the ability to correctly approximate the progress of the project. The simulation results is the completion time statistics estimated during data from Jira repositories. Empirical methods require a significant amount of data to statistically assess the impact of influencing factors to successful project completion. Conceptual models based on knowledge in the form of history of failures is represented in the form of a knowledge graph. The model consists of dozens of concepts and connections between them, provide understanding processes and events to prevent risks in a timely manner. Conceptual models are adjusted using expert knowledge. By analyzing the development process of real projects based on relative proximity and comparable goals. The Groudon theory is used to generate explanations regarding the compliance of the project state with the requirements and to reconstruct the sequence of events that can cause software failure. Planning strategies based on software analytics and empirical assessments are generated automatically to predict software failures. Current planning actions are generated in the form of rule-based explanations and associated risk thresholds. Problem statements, algebra of algorithms and fuzzy logic in software reliability analysis. The software reliability model is based on description of events related to occurrence, detection, and removal of errors using the modified system of Glushkov's algorithmic algebras. We consider the following types of operators. Working operators involve introducing errors. Checking operators correspond to the stages of testing and detecting errors. Correction operators correspond to debugging stages and at removing errors. We consider the following algorithmic structures. The linear structure describes a sequence of works without feedback. The alternative structure describes the process of working, testing, revision without feedback when errors are detected and immediately removed from the system. The iterative structure describes the process of work, testing, correction with feedback when new errors can be introduced during debugging stage. The logical algorithmic description of the software development process is considered as a fuzzy knowledge base. The process-oriented model of reliability. The inputs are reliability and time estimates of working, checking, correction operators obtained based on expert and experimental information. The outputs are two classes, correct
I'm sorry,
and incorrect.
We only see the first slide of presentation.
I'm sorry. And can you see now?
The first slide. Oh, yes.
Now?
Okay, now we can see other slides. Thank you.
The reliability model of operators and logical conditions. The inputs are the possibility of occurring errors of the type J. The outputs are two classes: correct and incorrect execution of software functions. The aim of the work: to propose a logical algorithmic model of software reliability which allows managing the risk at the stages of the development process. Improving substitutions are introduced into the logical algorithmic model. It defines the quality of the execution of working, checking, and correction operations. Improving substitutions determines the allocation of efforts. To reduce the risk of introducing errors during the development stage, to reduce the risk of missing errors at the testing stage, to reduce the risk of leaving errors in the system, or introducing new ones at the debugging stage. In Glushkov's algebra of algorithms, the development process is described by a linear structure. The process of testing and debugging of the model I with the detection and removal of the error of the types J is described by the alternative structure work control revision without feedback, or the iterative structure work control correction with feedback, where the working, checking, and correction operators are defined below. The allocation of efforts is formalized by adding the improving substitutions into the logic algorithmic description. We denote the vectors of parameters that determine the quality of the execution: X for the working operators, Y for the checking operators, Z for the correction operators. The parameters X, Y, and Z are chosen in accordance with Sati scale and can be interpreted as frequency or thoroughness of execution of working, checking, and correction operators. We consider the generation of variants of the logical algorithmic model as inference in a formal grammar. We define the set of operator and logical functional units, terminals. We define the set of operator functional structures, non-terminals. We define the null version of the logic algorithmic model. Also, we define the set of improving substitutions for the working and correction operators, for the logical conditions, for the operator structures. The correctness of completion of the stage A is described by the system of fuzzy rules. If the working operator is executed correctly, or errors are correctly detected and removed during control and correction, and no new errors have been made, or errors are correctly detected and resolved during the debugging, then the stage is completed correctly. This system of fuzzy logical equations connects the correctness levels of the process and its elements included in the logic algorithmic description. The possibility of correct and incorrect execution of the working operators, the possibility of detecting missing errors when checking the logical conditions, the possibility of removing, leaving in the system errors, and introducing new ones during the debugging operator. Risk management using controllable variables is complex as follows. The risk of introducing errors is raised to the power x. The risk of missing errors when checking the logical condition is raised to the power y. The risk of leaving errors and introducing new ones when performing the correction operations is raised to the power x. Thus, we decrease the risks and we increase the fuzzy correctness of execution of working, checking, and correction operations. Execution time for the development process is calculated proportionally to the development time of the null version of the model I. Let us consider as an example the problem of assessing the risk of the development of a mobile application for image aggregation. The logical algorithmic description is presented in the slide. The algorithmic structures correspond to the stages of the development process, starting from A0 requirement analysis to A19 publication and support. Risk assessments when analyzing requirements and development technical specification. High risks are detected and removed by allocating efforts through working, checking, and correction operators. Design risk assessment, the next group of factors. For example, inconsistency with user requirements. High risk are marked and removed from the system. Risk assessment when analyzing implementation methods and architectural solutions. For example, neglect of expansion needs. The following groups of high risk are marked. Development and testing risk assessment. The groups of risk are marked, for example, design patterns mismatch, using wrong architectural styles. Risks are detected and removed by allocating efforts through working correction operations. Risk assessment in preparation for publication and support. The high risks are no resources for support. Critical bug fixes are missing. We also highlight risks, detect them, and remove from the system. The problem is to evaluate the project development time that does not exceed 16 weeks. Risk distribution of the development process of the null version and after allocating efforts on development, testing, and debugging is presented in the slide. We consider the following groups of risk. Risks of introducing errors, risk of missing errors, risk of leaving errors in the system, risk of repeated correction, and risk of completing the stage incorrectly. Then we predict the number of completed tasks using model cumulative flow diagrams. The decision to accept the task or return it for revision is made based on the execution of the working and control operators. The decision about the successful revision is made based on the possibility of correct execution of debugging operators. The decision about the successful completion of the stage is made based on the correct execution of the algorithmic structures. The proposed model ensures stable software quality management when the number of development tasks the tasks in development and testing remains stable, and the number of corrected queue is steadily decreasing. In contrast to clusters of factors influencing software reliability, we use time series approach for the development process with the M-array concept of errors. The number of model parameters is reduced to the number of errors types k at each stage A. To assess the risks of the mobile application development process, from 2 to 7 risk factors or type of errors were considered at each stage of the life cycle A0, 8, 19. Future research involves training the reliability model on experimental data in the form of history of errors and defects. This approach consists in building and training membership functions of fuzzy correctness for operators and logical conditions, as well as rule weights for the algorithmic structures. Training is carried out by transferring reliable elements of the description of the process and its elements from the training dataset to the logical algorithmic model. Thank you for your attention.